Hi, my name is Jared Wood. I'm a master's student at the University of Idaho, and today I'm going to be discussing with you ultrasonic testing as a form of non-destructive testing of components. Today I'm going to be using a GE USM Go ultrasonic tester. And before we get into it, perhaps we should talk about some basic principles of ultrasonic testing. So for ultrasonic testing, you have your recording device, which also sends out the signal to your transducer. Your transducer has a piezoelectric material or element to it, which receives an electric signal from your testing unit here, which causes it to oscillate and emit an ultrasonic acoustic signal. This signal goes in to the top of the material that you're testing, reaches the bottom material, and sends back a back echo. When that signal encounters defects such as holes, cracks, and the like, there'll be a reflection off of that, which is then recorded by the testing unit via the transducer. Some important considerations about this is the transducer selection. In this case, this transducer is approximately 1 centimeter in diameter, and it is a 5 megahertz transducer. The frequency of the transducer is important because the higher frequency, generally the higher the resolution and the higher the sensitivity of the signal, which means that you'll be able to more accurately and more clearly detect defects within your sample. There are some trade-offs with that though. Some materials, particularly cast materials, which have a large grain structure, the signal is reflected back at higher frequencies, so a lower frequency transducer is required. This means that you need to select your transducer based on the material that you're testing. Another phenomenon that you have with this testing is called near field and far field. Now, when you're sending out your acoustic signal via your transducer, you're not originating that signal at a single point, you're originating that signal across the surface of the transducer. What this means is that sound waves are going to be originating from multiple locations, and that means those sound waves are going to be interacting with one another and interfering with one another. The near field, which is a region that's close to the surface of the material that you're testing, is characterized by the interference of these sound waves, resulting in low resolution and low sensitivity in that region. Once it reaches a more uniform interference pattern, that becomes what's called the far field, and that's where you're going to be detecting most of your defects. Now, the surface of this transducer, of course, is not perfect, nor is the surface of the material that you're going to be testing. So that whenever you're testing, you're going to need a gel couplant on the surface of the material in between the transducer and the material to act as a transmission medium for the sound waves coming from the transducer. Now, this particular sample that we're going to be using today is a calibration block, or a reference block. It's made of 1018 steel, and it has a number of particular features to it. It has 3 holes drilled through the body of it, each of them a different size. Over here you have a small hole drilled. This is a different depth than these 3 here. These 3 are at a corresponding depth. And then here there's a large hole with an acrylic window that's been filled in there. So we'll be testing at all these locations to get a feel for how this unit works. Looking at the unit here, you'll see there's a number of different settings, one of which is the range. This setting here is what you want to have calibrated to the thickness of your sample. In this case, it's preset to 101.5 millimeters, which is the thickness of the reference block that I'll be using today. There's also down here sound velocity. This is going to need to correspond to the sound velocity through the material that you're testing. In this case, 1018 steel has a sound velocity through it of approximately 5,890 meters per second. This setting right here is for the frequency, and here's where you need to set your you need to set that frequency according to the frequency of your transducer that you'll be using. Alright, so now that our unit is set to the appropriate settings, we're going to take some couplant. Doesn't take much, a little blob there. And with your transducer, just spread that couplant across the surface that you're going to be testing. All right. So now, after putting the transducer against the surface of the block, the first thing we'll notice is these peaks here. I'm going to remove it here and put it back again. This represents the bottom of your sample. This is your back echo. That's the sound waves traveling to the bottom of the sample and then traveling back up. And this corresponds to the depth in the sample. The scale here corresponds directly to the range that we programmed into it previously. So this mark here is right at 101.5 millimeters. So now we can move the transducer across the surface of the block, and now we see here some peaks rising up. This corresponds to this first hole that we have in the block, and you can correlate down on this scale here and see that hole is right at about 32 millimeters deep into the sample. Now the size or the amplitude of those spikes there are going to correspond to the size of the defect, or in this case the diameter of the hole. And we'll see that as we move over to the second hole, as now the amplitude is slightly larger. And then we go to the third hole, and the amplitude is larger still. Again, the position of those spikes along this scale indicate the depth in the sample where the defect is. Coming back, now we're approaching the large window and the small hole. So now we see the large window approaching here, and here's the small hole. Okay, so this is the small hole. We can see that the small hole is at approximately 15 millimeters deep into the sample. We can see that the top of the window here, this large perturbation there, is approximately 47 millimeters deep into the material. And we can even see all the way to the bottom to about 92 millimeters. Where's the bottom of the window here? Well, that covers the basic operation of the unit. There are, of course, alternate configurations that can be used to adapt to particular circumstances. Most notably may perhaps be the use of an angled probe to send your ultrasonic signal at an angle throughout your sample. If you consider that if you have a vertical crack in your sample or some other vertical defect, placing the transducer over the top of it, you may see an indication of where the top of that defect is, but it will likely be unclear as to the character of that defect below that point. However, if you use an angled transducer, you will be able to see from the side and gain information about the depth and other characteristics of that crack via that avenue. This is particularly useful in testing of weld joints, where the weld metal over the top of the surface of the sample is irregular, of course, and would prevent the use of a typical transducer directly over the top of it. Well, that concludes our demonstration for today, and thank you so much for tuning in.